Occasion, nothing. Last week I started this and we have cakes, pastries for the They were. It's end. It's finished. Being quenched by money. So last time I spent a lot, so the dean said no, not this time. We have to pitch in some of the faculty.
But I thought this institute always has this thing that we are not spending.
Thank you for coming. Okay, I think, are we ready? Not ready? Okay. Okay. Chandrayaan. Yeah. So, for all of you, just an announcement. We will have to finish this colloquium by 5:15 because sort of a historic moment is going to be telecast live in this auditorium as Chandrayaan 3 does a soft landing on moon. So we will watch that together after the colloquium. Okay. So. Hey, you guys can come forward. Shubhadeep. Yes. Your place is always there. Yeah. Hey, you can introduce question. Still a problem? वो छोड़ दो. It's okay. You don't have to worry about that right now. More. Go to more. Go to more. Okay. Then just put it down. Just put it down. It's okay. It will go away. Don't worry. Okay. Yeah. Okay.
Yes, thank you. I'll put it here.
Yeah,
okay.
It is Ciliberto.
Ciliberto. Okay, thank you. Yeah, okay, thank you.
Okay. Yeah, you can take a seat.
Yeah, okay.
Okay, so we are ready. So, welcome back to the Wednesday Colloquium series. Of course, those who are new to the series, just a quick refresher. This is the oldest science communication series in the Institute, started by our founding director, Professor Homi Bhabha, who used to visit on the Wednesday and meet the faculty and listen to one of the experts who would be visiting TIFR that day for a colloquium. So it has been a very long-standing tradition, and we've had fantastic speakers, and also this colloquium series has yielded collaborative ideas within the institute, not just with the speaker, but within the institute. So it's been a very, very productive and gratifying series for us, for students and faculty. So please do keep coming every Wednesday. The next series of flat out 8 weeks are full with speakers from all over the world. So thank you. We have, of course, our speaker today, Professor Sergio Ciliberto, if I got the name correctly, from Econ Normal in Lyon. So without further ado, I will hand over the mic to Professor Shamik Gupta, who has been the official host, to introduce Sergio.
Yeah, so it's a real pleasure to have Sergio visiting us here. So Sergio is an experimental physicist and a leading experimental physicist working in the areas of nonlinear dynamics and statistical physics. So he has been the research director at the École Normale Supérieure in Lyon. And since 91, he got his PhD in 1977, has been a postdoc in France, Italy, US, and so on. And then he has been at UNS Lyon since 1991. Now he has done experiments in a wide variety of topics, starting from quantum optics, turbulence, friction, track dynamics, and in more recent years in statistical physics of out-of-equilibrium systems and information theory and thermodynamics. He has recently meaning a couple of years back, he won the prestigious Statistical Physics Prize of the European Physical Society. Besides, he has been a member of several committees, and the European Research Council. He has been the chair of one of the panels, and so on and so forth. But I would like to add my personal note, namely that I was a postdoc in the same department where he is now at the moment. And well, I'm a theoretician, but over the years that I was there, I had the chance to discuss theoretical aspects with him. And every time I discussed with him, I got something new, a different insight into my own work. So it's been a real pleasure to have him here, talk about his recent work on experiments on Landauer's bound and the energetic cost of information. So what you said.
Thank you very much for this very kind introduction, and thank you for the invitation. It's always a pleasure to be here. I was in Bangalore last week and now here, so it's always a pleasure to see all the friends in India. So this when Shamik kindly proposed me to give this talk, I choose this argument and this subject, and okay, the title has been announced already by Shamik, and okay, so the first things you wonder whether these two pictures has to do together. This is the Google data center, and this is just a sketch of the the Maxwell demon that. On which I will come back later, okay? So when you look at this title, you immediately think to plot like this, for example, the Kumiri law that tells you how much it costs to drive for each flop of computation, how many watts are needed, okay? I will go back on this plot at the end, and then, okay, you can also think to an incredible amount of total energy, electric energy that is needed in order to compute our data and to use a computer. So these are just, for example, a plot of the data center, user, etc. But at the end of the story, I don't want to talk about this, but much more fundamental questions. And the question that I want to discuss with you is there a fundamental law of physics, especially thermodynamics, which connects energy with information? Okay, this is the first question. And the other question is, can we perform a logic operation with an energy cost? And many physicists actually have studied this question. And for example, Maxwell was the first, then Sizzler, Brillouin, Shannon, Landauer, Feynman with the famous ratchet, and so there are a lot of famous physicists of try to analyze this problem. So during my talk, I will first discuss the second principle of thermodynamics and Maxwell demon, the connection between the two. Probably I will say very obvious thing for many of you, but as Shamik told me that the audience is quite large, so coming from this discipline, I want to establish, let's say, a common language. And so the second, I will go to the paradox of Maxwell-Demon and the Landauer bound. Then I will show you some experiments that are not necessarily by our group. And then, okay, I'll give you some conclusion, okay, and the importance for applications, okay. So let us start. I'll start also for the first principle. We are talking about thermodynamics. This is obviously simply just energy conservation that tells you that the variation of internal energy between two states A and B is equal to the work done for AB minus part of the heat that is dissipated in the heat path. Instead, the second principle is more subtle, in the sense that the second law is a statement about irreversibility, okay? And it is usually stated in physical terms of impossible process. And now, as you know, of course, there are many statements in which you can define the second law thermodynamics. And the one in which we are interested in is the statement by Kelvin, that is, no process is possible in which the sole result is the absorption of heat for a single source and its complete conversion into work, okay? Remind this definition because it's the one that we use. There are other definitions for the second principle, but this is of my interest. Then, okay, there is the question of the entropy, okay? As you know, the entropy in thermodynamics is defined as the ratio of the heat exchange with the heat bath. Okay, and then we know that the second principle means that the total entropy on a transformation has to be larger than zero, the variation of the entropy. But there is also, as after Boltzmann and Gibbs, there is also a statistical definition that, as you know, the definition by Gibbs is just this one. It's a sum over pi log pi, where log pi is the probability of having a particular microstate that corresponds to a macrostate, okay? But then when you look at on that data analysis, certainly, you know the beautiful work done by Shannon, who also defined an entropy that is an information entropy, and actually tells us how much information is contained in a signal. And you see that formally, these two definitions are the same, okay? This, again, there's a probability of having certain sequence. And so the other question that is important now is thermodynamics entropy. Is thermodynamics entropy the same than information entropy, okay? Now, the third ingredient that is needed for what I would say is the Brownian motion, okay? These are typically what you see when you look small colloids of 2 microns diameter. This is the movie is 10 times faster of the reality. And so you know that because of collision of molecules around, the colloids are shaken as we see there, okay? And typically the energy is kBT, okay, that everybody knows here that is a small energy. And but what is interesting at this point is 10 to the 6 times smaller than the energy used in a computer to compute a bit, okay, to compute a bit. Good. So let's now go, after having given this definition that are of interest for this talk, let me recall you rapidly what the problem of Maxwell-Demon is. Certainly you have seen this in your thermodynamics lectures, but okay, let me fix the idea. The idea is the following. You start from a container that, of course, contains slow, the blue one, and fast molecules, okay? And then you put a wall with a gate, okay? There is also the gate, a daemon that control the gate. It can open and close. And what it does, it look at the molecules, okay, and then it opens the gate for let the fast molecule to go on the left, and it closes, and it allows it again. It opens again to let the slow molecules to go into the right. At this point, what it has done, it has produced a difference of temperature that can be used to produce work, okay? But you see that there is the contradiction of the definition of the statement of the second principle, because I said that it is impossible to produce work from a single source, because actually I started from a single, for a given temperature, okay? So the question is where the problem is coming from. The problem, and in this, there were a lot of discussion about that. The first explanation was given by Leo Szilard, and later in the 50s by Léon Brillouin. What proposed Szilard is a very smart idea. So he said, let us take a single molecule gas, okay? And then you see now the task of the daemon is very simple, because it can decide if the molecule is on the right or on the left. Now, if he look at the molecule and then he find it on the left. So you see, put a piston, and then you see the collision of the molecules allowed to do some work and to change the height of the weight. Okay, so you produce works against gravity. Okay, and now when you have finished, you start again putting the weight on the other side, and so on and so on. Okay. So the point of Szilard was actually the good point, because he said, okay, the daemon indeed it seems that it has to do work, but it has to do measurements, okay, and that's to detect where the particle is. And then it's probably, this is the point that you need some energy in order to do measurement, okay. So this was also discussed by Brillouin, Landauer, etc. Okay. So what I want to stress now, that modern technology and stochastic thermodynamics that we will see allow us to transform Gedanken experiments like this in real ones, as you will see. Okay, so let me now go to this nice picture. So first of all, the experimental realization of the Maxwell daemon. This was done in 2010 by the Toyabe group in Japan, and I'll show you what they've done. This is a schematic, really is the principle, the experiment is a little more complex, but the idea, this reproduces quite well the idea. Suppose that I have a small particle and that moving on a staircase, the particle is so small that it's sensitive to fluctuations, okay? And you have seen, I've shown you the movie of the Brownian motion. So the particle, of course, in average will go down, but being sensitive to the collision of the molecule, sometimes it goes up. Okay, and now here is the point where the daemon come in, because you look at mean on daemon, and now you see the choice is very simple. It's almost similar to the Szilard engine that I've shown to you. If the particle goes up, you put a wall. If a particle, and then avoid that the fluctuation of the particle goes down. And now you see, just thanks to the thermal fluctuations, you see, you climb the stair, and then, of course, you can do the work by the particle that is falling down, okay? But so you are in trouble here. How is possible? Because actually you are producing work from a single source. But Toyabe, actually, Sagawa came with this simple equation. What this is telling you? This is really an extension of the second principle of the thermodynamics, because what we learn in standard books of thermodynamics, that the work needed in order to change the free energy of the system from a state A to the state B must be larger or maximum equal to the free energy that you produce. But then you realize that you introduce information on the system just because you're doing measurement. And now you see what is the relationship within the Shannon entropy. You see that now information is quite simple because it's just the probability on going to the right or the left. And just apply the equation of the Shannon entropy that was just the sum of P log P. You see that this is the expression. And so actually in this experiment, they proved that the work that was produced by the system is always limited by this information, okay? So this is a strong connection between thermodynamics and information, okay? This was the first issue. So let me skip for the moment this plot. I will go back later, but I wanted to show, I don't go into this experiment because it will take 1 hour only to explain. But roughly speaking, a beautiful experiment by the group of Jukka Pekola in Oslo. And okay, there is actually a daemon that controls a single electron transition, the flow, okay? So what it doesn't matter. But what I want to stress, this is a beautiful measurement done at a few millikelvin. You see that it can measure the temperature of the daemon, okay? And what you see here, that when the daemon is on, okay, you see that the temperature of the daemon is increasing, okay? Whereas when the daemon is off, the red line is the red line is just the temperature of the daemon, that the other temperature, so that the daemon actually is cooling the system thanks to the thermal fluctuations. The important result of this, you see that when the daemon is off, okay, you have 0 temperature for the reference. And then the daemon is heating when is analyzing the information. So it means that the daemon is actually doing work in order to perform the operation. Okay, I'll go back on this. Okay, now let me do the counterpart. So this is something that on which all next slides will be dedicated. This is actually the measured energy that is needed in order to erase a bit of information, okay? And then you see that if you do that very slowly, you arrive to this limit, okay? And this is called the Landauer bound, okay? So let me explain what the Landauer principle tells us. So it tells us that any logical irreversible transformation of classical information is necessarily accompanied by the dissipation of at least kBt log 2 of it per lost bit, okay? So what is a logical irreversible transformation? For example, all the Boolean operation in which the knowledge of the output does not allow you to know the input, okay, this of course is an irreversible transformation. The most irreversible transformation that you have is of course the reset to 1, okay? And so, it is, in this case, it's rather easy to show that in order to reset a bit, you need the kBt log 2, okay? I'll show, before showing this, I want just to stress the Landauer principle is a central result that exorcises the Maxwell demon. And although it's been criticized, however, it is measured in several experiments, okay? The question is how the Landauer bound can reach in the experiment, and does an experimental physical protocol allows us to reach the limit, okay? Then we follow Bennett on a very, very old idea of 1982 okay, the reset to 1 operation. So I will show you where the log2 is coming from, okay? Now, the idea of Bennett was the following. Suppose that you have a particle, okay, which is confined in a double well potential. And then you say, so this is sort of memory. And then you say that at the beginning of your experiment, the particle can be in 0 or 1 in 0 1 with equal probability. So it means that the initial entropy of the system, if you repeat the experiment many times, is kb log 2. And now you try to apply a protocol such that at the end of the protocol, the particle is in the well 1, okay, with probability 1. So the entropy in this case will be 0, okay, and thus you see that you have, during the transformation, you have a negative entropy difference. So what does it mean? It means that if I do a quasi-static transformation, okay, it means that I have to produce an heat equal to TTTS. Delta U is 0, okay, from the beginning and the end, because the potential is the same, okay? And so it means that in order to erase the bit, to perform this protocol, I need to produce a work which is larger than kBT log 2, okay? How can this possible be realized experimentally? Okay, so there are several methods. One method that we used, you will see there are many other possibilities. So you have, for example, optical tweezers that allows you to trap, for example, transparent particle inside the fluid. So you have a laser beam that is focused, and you can show that colloidal particles are attracted to the point of maximum intensity in this point with the potential that is harmonic. Okay, then, these are just pictures of a colloidal particle trapped by 4 laser beams. And I remind that Askin got in 2018 the Nobel Prize for having invented this technique of optical trapping. What we are interested in is now what is happening if you put 2 beams one on the other, and then you see that the particle that we see here is jumping from one position to the other. So you have produced this, you measure the position of the particle, then you make the probability distribution. This has to be equal to the exponential of the potential trapped in the particle, and reconstruct the potential looking at
Sergio, sorry, go back to the experiment, please.
Yeah.
So here, you have the 2 focused beams.
Yes.
Do you have a dual focus?
Yes,
dual
dual focus one inside of the other, okay?
Okay.
Yeah.
So that's why you have a
Yes,
sort of
the
a 2
particle,
potential.
yes, I did not explain. Thank you for the question. Actually, the particle is attracted by beam, but then thermal fluctuations allow the particle to jump to the other metastable position. So the particle is jumping from
Between the 2 isoenergetic traps.
Yeah, absolutely. Isogenetic trap. Actually, you see that this is the potential that you reconstruct that is trapping. Okay.
Right. And typically, what laser power you use to?
Oh, a few milliwatts.
Few milliwatts.
A few millis. Yeah.
And what is the nature of the bead? What is it? It's like a silica bead, or?
It's a silica bead. Yeah, this is exactly a silica bead in water. Okay. So the only constraint is that the index of refraction of the bead will be larger than that of the surrounding fluid. Okay, otherwise you don't.
And you would like to trap it in one focal spot, right? Out of the 2, that's what you want to perform the operation.
Yeah, but okay, if you put that far away, as you see in the previous picture, you see that here, for example, I have 4 beams and they are separated. There are 4 beams, 4 particles that are separated. Okay. Other questions? Okay, that is good. Okay, so as I said, you can you reconstruct the potential like this, and then, for example, you can check that you have a barrier of 2 kBT, and then you can check the Kramer's rate, the time that the particle takes in order to jump from one point to the other. Okay, so now I have my 2 wells potential, as in the case of Bennett. Okay. And okay, what I didn't say that the stiffness of the beam is proportional to the laser beam. So by modulating the laser beam, I can change the stiffness of the traps, okay? So now let us see the kind of protocol that I can use. Now I've increased, if you want, the laser power, okay? And so you see that the barrier now is very high, so the particle is almost trapped in the initial state, okay? Which of course can be 0 or 1, okay? But suppose that I start from 0, okay? So the first thing that I do in my protocol will be the following. The first thing that I do, I reduce the barrier, okay? So I let the particle to jump, okay? Then what we do, we gently incline the potential, okay, with a horizontal force, okay? So slowly the particle is pushed towards 1. And then after having reached the maximum, what I do, I increase very fast again the barrier, the particle is trapped again, okay? So now you see that if I start from 1, it doesn't change anything, because at the end of the protocol, okay, I will always be in 1. So I realized what Bennett proposed to do. Okay, so for example, this is a typical movie that you have. This is the particle on the left. You see now, this is the trace. You see the particle oscillate there, and at a certain point it jumps and it remains in 0. The same if you start from 1, okay, you see that the particles stay there, a big fluctuation bring it on the other side, but then of course the force is pushing it in the final state that you want, okay? Now, a short summary of stochastic thermodynamics. Now you see that the trace of the particle is very random, because actually it's doing Brownian motion inside the trap. Okay, and so now this I follow Sekimoto. The motion is described by the double well potential plus an external force that is the force that is pushing the particle, and it is easy to see that you can write. If you can write the integral or on a time tau, for example, the time of the protocol of the potential difference during this time tau and the work performed by the external force on a time tau and the heat that is dissipated on the heat bath. And now you see, of course, that there is some part of the work that is done by heat bath. Sorry, for those that these are just the noise term. So this is actually coming, this decoupling with the bath that is to actually produce the Brownian motion. Okay. So you see that the important point to notice this, all of these are fluctuating quantity just because you are in a noisy environment where the noise is given by the fact that there are all these molecular collisions on the particle. So what I can do now, I can do the process 0, 1 going 1, 0, 1 going 0 in order to increase the statistic, of course. So I can compute the force as I am ramping the force. I can compute the work done by the ramp of force that is here, that I call the WF. The effect of, you see that the potential part actually don't need to compute, because before I reduce the barrier, then I increase, this is conservative part, so it doesn't, there is no work done on that, so I did not decompute. But you know that that is interesting to see that this is a probability distribution of having a certain work if I repeat the experiment many, many times. And now you see that there is even negative tails of the work. That means that the collision are so important that the particle actually is moving against in the opposite direction in which the force is pushing. Okay, and now you see immediately that this is the case. This is a Landauer limit. And you see that the mean of this particular experiment is close to that, but you see that the fluctuations actually are helping a lot on reducing this mean. And now what I can do, I can take the mean value And I can plot it. There was the original plot that you can see. This is Q, but you know that the work is the same as a function of the time in which I'm ramping the force. And now the important result to take into account in this plot is that I go very, very, very slowly, okay? And then you see that all the points are above the Landauer limit. That is, I have an asymptotic behavior in which the work needed to do the protocol, it goes to the Landauer bound, but does not overcome this bound. The green point I will explain. I mean, is not a mistake. It must be there, and I will discuss in a moment why. Okay.
Another question: these timescales have no meaning to us unless we know what the timescale of the experiment is in terms of when you make it slightly tilted. When do you relax that tilt? What are the timescales associated with that?
This is just the full experiment. The full experiment.
So that is
I have the cycle. You have seen the protocol, reducing the barrier, incline the potential, increasing the barrier. This is the full cycle. Okay.
A minute, less than a minute.
Yes,
right?
40 seconds. So it's very, you will see at the end they can do much faster, but in another system, okay? So this is, okay, and then there is another important point. I will tell you because it's interesting point of view of from the okay, sorry, there was a question. Yeah.
So there's like this debate on the internet with people arguing Landau's principle is wrong, etc. And one of the papers they quote is this one from 2016 in Nature Communication by somebody called Soares, Lopez, and Neri. And there they claim to have gone below the Landau's bound. Are you familiar?
Yes. Okay. It's no sense. I mean, this article. I mean, the feeling is, I mean, the answer is short answer is no sense.
Yeah, I mean, I went through the paper. I think what's happening is that the tail of the distribution that goes to zero.
Yeah.
Some of those are being or below zero. Some of those are being sampled and being presented as a.
Yeah, indeed. I mean, this is exactly. For example, one has to pay attention to what is the success rate. Okay, and now okay, indeed.
So it has to be the average of a large number of.
First of all, it should be large. I mean, this the point at 40 seconds took 1 week to get it. Okay, because 40 seconds, we are thousands of tests of 40 seconds. So it's took a very long time, of course. Yeah, a very long time. And okay, so now let me explain the problem of the success rate, which is very important. Because what is the success rate? Because you are in a noisy environment, so sometimes you find the particle in the wrong position. Okay. And so you see that we measure the success rate. And of course, it depends how much you incline the potential. Okay, it's not surprising. Okay, but surprisingly, our best success rate is 90, 95, 96%. And as an explanation. But what I want to stress in this plot is that you see that the fact of being above the Landauer bound is related to the success rate, okay? Because by changing the maximum force, I can actually modulate my success rate. And now you see that the green point is actually this point, okay, where the success rate is is very bad, okay? And so here there is an explanation because actually you can prove this equality that in the case that the success rate is not 1, there is a correction that can be proved that starting from the Janskinski equality. And now you see there is a correction because immediately you realize from this equation that if the success rate is 50%, of course, the Landauer bound is 0 because you have a fully indeterminate system at the beginning, a fully indeterminate system at the end. So there is no gain. And the work that you do is, of course, 0 because there is no information. So I think I plot this about the success rate because it really illustrates that is very important to check all this kind of problem. And then, okay, there is another interesting problem. You see the blue line. The blue line is another interesting feature that was discovered by Sekimoto in 1997. And so Sekimoto asked a very simple question. We learn in thermodynamics that in order to measure exactly the free energy difference, we have to do a quasi-static transformation, okay? But the question that Sekimoto asked, in spite of the fact that I can do a very slow transformation, I do that in a finite time, okay? So what is the first correction to the free energy if I do that in finite time? And then he came out with this. Of course, B depends on the system, is not independent, but the first correction should be in 1/tau. And also you see that in this case, you see that delta U is 0, then our free energy is just minus T delta S, the change of entropy. And so you see that the work and the heat must go as kBT log 2 B over tau, and this is actually what is happening, okay? Okay, so there's a simple question. I mean, I can go very fast on this. The point that our success rate is not 100% is just due to the fact that you have a finite barrier. So sometimes the particle taking into account that we do very, very long experiment, sometimes the particle has the time to overcome the barrier because of the Kramers rate, okay? And so you find the particle in the wrong position. Indeed, we test numerically, and it happened that if you change the barrier from 8 kBT to 15 kBT, you see that you change the barrier from here, the success rate from 95% to almost 100%, okay? Now, so let's summarize what we have seen till now. So our experimental results indicate that thermodynamic limit to information erasure, the Landauer's bound, can be approached in the quasi-static regime, but not exceeded. The asymptotic is reached in 1/tau, and the success rate is smaller than 1 just because our barrier is not sufficiently high. Then thermal fluctuations, as you have seen, plays an important role because they're actually helping us in overcome the barrier during the protocol, okay? So this is just, okay, this is just a summary of other experiment that has been done later on in a very different system. This was an electric system. This is again a colloidal particle. These are spin system, and then okay, other operation, and then I think there is also a quantum version of that with done with complex molecules. Okay, so I don't go into this, but the question that I want to analyze is the following. Of course, I've shown you that the Landauer bound can be reached asymptotically, but then the question is the following: can the Landauer bound be reached in short times? And the answer is yes. For example, if you use optimal protocol, there is a beautiful theoretical work of Orell and collaborator Krzysztof-Gawęcki and other, in which they compute actually. Inspired by our experiment, they compute what should be the optimal protocol in order for a fixed time to minimize the energy which is needed, okay? And so they came out with very complex protocol that are difficult to realize experimentally, but at least you have some possibility of reducing this point by applying optimal protocols on the system, okay? But there is another way to go fast. And the way is to use another system instead of colloid. This is a cantilever, okay, that of an FM. So here inertia is very important. Actually, you see this is the resonance. This is a spectrum of the thermal fluctuation of the system. Now we have a resonance of the system. And I don't explain why, because the technique, but actually you can produce a double well potential that you can perfectly control. So now the system has inertia, as you see, because there is a strong resonance there that in the case, and then the system now is biquadratic. Actually, the two wells potential that you produce is just a biquadratic potential like this, okay? And now, I mean, to make a long story short, okay, what we did is a different protocol that in which the success rate, I mean, doesn't matter what you do, is always 100%. So the idea now is the following: you change protocol, you start again from a double well, and the particle can be either on the left or on the right. So what you do, the first operation, you merge the two wells in order to get only one wells, okay, one well, and then you gently move the well in the original position, and once you have in the original position, you create again the double well, okay? This is what we do. And what is interesting here, you see, this is the work produced by on the system to do this operation, okay? This is a work as a function of time. Now you see that it's very interesting to notice that all the work is done during the merging. That is done during the change of entropy of the system. The other, of course, can be done as low as you want, and at the end of the story, you don't do work when you re-put the well in the original position. And this has the probability distribution of the work, and actually you see that the work during this phase is 0, and the only work is coming from the work performed during the entropic phase, let us call like that. And now again, what you see that W and the heat, okay, goes asymptotically towards the Landauer bound. Again, in one over tau, where tau is all the length of the protocol. Okay, and now it's interesting to compare the two experiments, one with optical tweezers and the other with an atomic force microscopy, a small cantilever. Okay, a micro cantilever, and now you see that. Just changing the system and going to a system in which the inertia is actually very important. So you scale the time of the apparatus, and you reduce the time to reach the Landauer bound of 2 orders of magnitude. So I am almost finished. And so I hope that I convinced you that indeed, in order to erase a bit of information, is a strong thermodynamic limit. And what is this useful for? I go now to this plot, to Comeri law, that is the computation per kilowatt hour as a function of the years. Okay. This follows this law, okay, that you can, for example, enjoy yourself in extrapolating, okay? And now you see that if these curves continue to grow like this, you will touch the Landauer bound at in 2060. So, yes.
With semiconductors reaching 3 nanometer, people are talking about the Moore's law breaking down, right?
Sorry, I didn't get your
with the semiconductors reaching the small 3 nanometer bound, there's a lot of conversation about the Moore's law breaking down. Or maybe the slope will change. Do you think that will happen here also?
I don't know. I am probably convinced. I mean, I am just playing the game. Probably this curve will be into bend because we are almost on the limit, but well, we are not aware of probably other technology that allows us to continue this curve. So this is just, I mean, a game that we play. Okay. So indeed, you see that at a certain point you will touch the limit, so we will have no space for improvements in somehow, because you reach what thermodynamics tell you that you cannot overcome, okay? So, of course, this limit, kBT log 2, is a remote quantity of energy. And for example, it has been estimated, for example, in feedback process in biological system that where, okay, there are complex feedback, and you see that indeed the amount of energy is conceivable to with this limit, okay? It goes like that. Okay, so let me before concluding and give you the final message. Let me thank all the collaborators: Antoine Beru, who did the experiment on the optical tweezer, Eric Lutz, who was the theoretician of the group, Artem Petrosyan, who constructed the optical tweezer, and then Ludovic Bellon, Pereda, and Dago for the experiment with the cantilever. Okay, so after having thanked my collaborator, let me give the main messages of what I said. There are only my talk can be summarized in these 2 lines that I hope you will keep in mind, and that are the important message. So what I've shown to you that Maxwell demons allows us to produce energy from information. Okay, this is the first statement. The second statement: information needs a minimum energy in order to be processed. That is the kBT log 2 of Landau bound. Okay, and then if you remember the very nice experiment of Jayuka Pekula, in which we see that the demon is actually eating when it's processing information, the point is that one has to keep in mind that the energy gain from information is always smaller or equal than the processing energy. And the demon, of course, cannot overcome the second principle, because in order to analyze information, okay, he has to do a lot of work, okay? So with this, my talk is strongly inspired by all this article. And so thanks you for your attention. So we have the time to see the language.
Thank you, Sergio,
Yeah.
for the very interesting talk. Are there questions for Sergio? Yeah.
Very nice talk. Can you please go back to that page where the particle was trapped in a laser trap, and then
Yeah, so let me do, yeah, let me do faster because yes, it should be, I think you this one?
the next slide,
Yeah. This one?
yeah, the next slide.
The
Next slide.
next slide, okay. This one.
Yeah. So my question is the graph on the down of the
Yes.
page. So here you were like you started from the position 1, and then you like shifted this potential. And,
Yes, I incline the potential as I shown, like this, okay?
Yeah.
Okay.
and so I am asking that why there is that deep in.
I mentioned that very briefly, but thank you for a question. This is an extremely important question because actually, you know, I actually pushing towards the position 1, okay? But the particle goes in the other direction. And so what does it mean? It means that for statistical for the collisions of the molecules that are on the side, actually it moves on the opposite direction, and so the work is negative in this case. Okay, and actually you see, if you remember the probability distribution of the work, that this kind of events are those are giving these negative tails. So each time the particle moves in the opposite directions, okay, because it's a strongly fluctuating environment, because there are the particle is actually performing during the protocol Brownian motion inside the trap.
Yeah, there's a question in the back. Sure.
So I mean, when you have control, right? You change the temperature and basically effectively you can control the noise. And in the right, in this experimental setup, I don't know.
Yeah, the answer is in this system, no, because you are because in any case you are in a liquid, you can change 10 degrees, but you change 10 degrees are 300, so it has no interest. Okay, but I answer to you, and in the cantilever actually there is a very nice effect that I did not describe. Now the system is highly underdamped because it is in air, and they could put even in vacuum. So the exchange with the heat bath are very, very weak. And now you see that if you perform the protocol too fast, the kinetic energy of the cantilever is so high that you have an effective temperature that is by far by at least almost a factor of 2 of the real temperature of the system. Of course, then it relaxes to equilibrium, but during the protocol, the system can heat. And now you see that indeed, the lower bound that's we to correct by this, if you correct with this effective temperature that you measure, you get that you see that it's shifting the bound.
Yeah, I see. I mean, there's a similar, I think there are some ideas with active matter, like you can effectively
but
like break the bound.
Is not exactly the same because
I know, but
because indeed here is just the kinetic energy that becomes so high that the equivalent temperature due to the kinetic energy is by far larger than the heat bath. Okay, because the system is strongly isolated during the protocol is so fast that there's no time to exchange with the heat bath. So you are almost adiabatic at this point. So
yeah, I mean, in the previous one, if you had some active particle which is transferring energy.
Okay. I have a quick question. So you said you were searching for fast time scales, Landauer bound experiments, right?
Yeah.
So have you looked at chemical systems, just chemical systems, where things could be very rapidly achieved in a two-level ideally?
Okay, the quantum version was done in molecules, so
the quantum version was done in molecules.
But I think was low too because was low.
What would be the time scales of that?
You said we can check. No, was later. I don't know if I put, but I mean it was not really very fast. The fastest actually we check is our cantilever. That is at the moment. But then probably let us see. No, I have not I didn't put.
So that is milliseconds.
But
that is milliseconds. Milliseconds.
Our is milliseconds.
And the cantilever is even faster.
The cantilever is milliseconds. Right?
But you can do these things in much faster timescales in nanoseconds with chemical systems, isn't it?
Probably yes.
It's very simple. You can have these ammonia-like molecules which can do this.
Probably.
Okay. Fine. Fine. Any other questions?
Yeah. So the definition about Landauer's principle.
I cannot hear you. Sorry.
The definition of Landauer's principle. There you mentioned the information has to be classical. So is it necessary that the information is classical if it is quantum information?
No, you can define also quantum information. Depends. I mean, what you're looking at. Okay, this experiment you were mentioning is on quantum system. You see, this is quantum Landauer erasure with the molecular nanomodel. Yeah. No. Then okay. Yeah.
But this bound applies only for an average of a large number of.
Yeah, absolutely.
It's essentially a classical statement.
It's a classical statement. Yes, you're right. Yeah.
So I also just wanted to get your opinion on one thing, since you showed Shannon entropy and work on some.
Yeah.
Recently, there's been this news, quite a bit of discussion about something called assembly theory and the assembly index. Are you familiar with this?
No, I don't know. No. Okay, I will be glad to discuss with you about that. Yeah.
Okay. Well, yeah.
So about this 1 by tau, this asymptotic limit.
Yes.
Can it be understood in any other way, like this 1 by tau be?
Okay, now you have to look at the Sekimoto paper, and this is just I don't think there is a by hand explanation that you can do, but you see that it shows that indeed the phase correction that you do when you do the measure of the free energy difference between two states. If you do that in finite time, of course, longer than the relaxation time of the system, then you have 1/tau behavior. Okay, so this is the first correction. That should be general. The only thing is the coefficient B on that.
Okay, well, in the interest of time, and we'll all, as an institute, like to watch the soft landing.
Yeah.
We will conclude the session here. Let's thank Sergio once again. And we have some refreshments outside in the canteen. So please do care to join us. And thank you all for attending in big numbers. Please keep repeating this next week as well. Thank you.
Till tomorrow night.